السلام عليكم ورحمة الله وبركاته. يعطيكم العافية شباب وصبايا. Our video for today is about fluid mechanics, part 1 from chapter 13. At the beginning, let me remind you the states of matters. As we all know, states of matters comes in liquids or solids or gases. In addition to plasma state, but we do not care about plasma state in our level. Therefore, the fluid can be defined as a non-solid matter in which the atoms or molecules are free to move. In other words, we are talking about substance that continually flows under an applied of external forces. From this definition, both liquids and gases are considered to be fluids. In a liquid, we can say the following. Groups of molecules can move relative to each other, but the volume remains relatively constant because of the strong cohesive forces between these molecules. As a result, a liquid takes the shape, as you can see here, the shape of the container. On other side, for the gases, you can say the following. A gas expands until it reaches the walls of the container and fills the interior or the whole available space. This is because the gas molecules are very widely spaced, and the cohesive forces between these molecules is very small. As you can see here, some applications or areas of fluid mechanics, something like weather, piping and plumbing, artificial hearts, as you can see here. So in our chapter, or in this chapter, we are going to study and learn the basic steps or tools or ideas in the fluid mechanics. First of all, we are going to talk about flow rate. As you can see here, I have the following pipe with two different cross-sectional areas, or with entrance and exit, filled with certain fluid. Here, I can say the following. If the fluid, as you can see here, if the fluid enters the entrance of this tube, then there is an equal amount must leave the exit of this tube. Therefore, we can say or call this principle as continuity equation, or equation of continuity, which means the flow rate at the entrance equals the flow rate at the exit. As you can see here, the flow rate, or the mathematical or physical definition of the flow rate, which is the volume of the fluid which passes per unit time. So we can convert this into the following: flow rate, which is volume divided by time. And you know the volume is area times length. So you can say area times length divided by time, where the length divided by time is the velocity. So from here, the unit of the flow rate, it's obvious, meter cube per second. And as I mentioned at the beginning, the flow rate at the entrance, or at the beginning of the, or at the entrance, equals the flow rate at the exit. Therefore, we can say this flow rate is conserved, which means I have constant quantity. Therefore, we can say Q1 equals to Q2. And this equation is called equation of continuity, or continuity equation. At the beginning, here we are talking about flow rate, which is Q equals V, volume divided by average time, or area divided area times velocity. What given from this question is the following. the velocity of the fluid, which is 20 meters per second, the radius of the tube, which is 0.015 meter. Therefore, we can calculate the area, which is by r squared. And the question is about to calculate the flow rate, Q. So as I mentioned before, Q equals area or cross-sectional area times velocity. So we know the velocity and we calculated the area. So what we have to do is just multiply the amount or the value of the area times the value of the velocity. Second example, a garden hose of inner radius 1 centimeter carries water at 2 meters per second. The nozzle at the end has a radius of 0.2 centimeter. How fast does the water move through the nozzle? Okay. We have two cross-sectional area, A1 and A2, or A2 and A1, or AA and AB. In general, I would like to do the following. I will assume the hose cross-sectional area is number 1, and the nozzle is section number 2. Therefore, I can say Q1 equals Q2. From this one, the A1 times V1 equals A2 times V2. We need to solve this equation in order to calculate the second velocity, or V2, or the velocity through the nozzle. So from here, V2 equals to A1 divided by A2 times V1. But be careful, we are talking about tube. And the cross-sectional area for the tube is by r squared. So from here, V2 equals by r1 squared divided by r2 squared times V1. So the radius is given and the velocity is given. Do your calculations and substitute the values of each parameter. You will get the velocity through the nozzle, which is 50 meters per second. And you can tell the following from here: as the area increasing, the velocity decreasing. And it's obvious here, you can tell A1 compared to A2 is smaller than A2, but V2 compared to V1 is larger than V1. Third example, water flowing through a garden hose of radius 10 centimeter fills 300 liters bucket in 1 minute. Calculate, or what is the speed of the water leaving the end of the hose. Okay, we know Q equals A times V, cross-sectional area times velocity. The radius here is given, so it's easy to calculate the area. And be careful, the radius here is in centimeters, so you need to convert it into meter, which is 10 divided by 100, or 10 times 10 to the minus 2 in meter. So we converted from centimeter into meter, therefore we can calculate the area. But what given here is 300 liter per minute. In other words, this amount, or this value, is the volume per average time. So from here we can say the flow rate, which is volume divided by average time, and you have to convert from liter into meter cube and from minute into second. So now we can say the flow rate is given, and from the radius the area is given too. So since the flow rate and area is known, we can say Q equals A times V, and the velocity from here, which is the Q divided by the area. Second, a nozzle is now attached to the end of the hose. If the nozzle radius is 1/2 the radius of the hose, this one is kind of a key of my question. What is the speed of the water leaving the nozzle? We are looking for the second velocity, or V2. So we know A1 times V1 equals A2 times V2. Therefore, V2 from here equals A1 divided by A2 times V1. But be careful. The second radius here is 1/2 the first, which means R1, sorry, R2 equals to R1 divided by 2. In other words, R2 is 10 centimeter divided by 2, which is 5 centimeter. So from here, we can say the velocity, which is 0.64 meters per second. And again, you can see area 1, or the first cross-sectional area, is smaller than is larger than A2, but V1 is smaller than V2. Fourth example, a cylindrical pipe that goes from first room to the second one. The pipe at the first room has a radius of 4 centimeter and the speed is 0.25 meter per second. The fluid exits the tube in the second room with a speed of 1 meter per second. What is the radius in meter of the tube at the second room? At the beginning, or before we are going to solve this question, you need to know that we are talking about flow rate. Step number 1. Step number 2, for me, I would like to mark the first room with number 1 and second room with number 2. Therefore, I can say A1 V1 equals A2 V2. And since we are talking about tube and cross-sectional area, the area here is by R squared. Now, from here, by R1 squared times V1 equals by R2 squared times V2. But by with pi cancel out, and we are going to solve this in order to calculate R2. So from here, divided by V2 and take the square root, you can say R2 equals R1 times square root V1 divided by V2. V1, V2, and the first radius, all of these parameters are known. So plug the numbers, you will get the second radius, which is 2 centimeter or 0.02 in meter. If the water that exits a pipe fills a pool that is 3 meter depth, 20 meters long length, and 5 meters width in 3 days, what is the flow rate? We know that the flow rate either volume divided by average time or area times velocity, but the velocity and area is unknown. Now, let us take a look to what given in this example. I have the average time, but as an unit of days, and it's easy to convert from days into seconds. And here the dimension of the pool is given 2. So therefore, we can easily calculate the volume, whereas the volume is x times y times z, or in other words, length times width times depth. So 3 times 20 times 5 in meter will give us 300 meters. And the time here is 3 days, so we can convert it into seconds, where 3 times 24 hours times 60 minutes times 60 seconds will give us this amount. Therefore, the volume and the average time, now both of them are known. So go back to the main formula, which is the flow rate equals volume divided by the average time. We can find that the flow rate is 1.2 times 10 to the minus 3 meters per second. Example number 6. The volume flow rate through the first pipe is 2.5 times that of the second pipe. If the cross-sectional area of the first pipe is 1/2 that of the second pipe, what is the ratio of the flow speed in the first pipe compared to the second pipe. So in other words, we are going to calculate V1 divided by V2. So here we are talking about flow rate. And we know A1 V1 equals A2 V2, which is Q1 equals Q2. What I would like to do is the following. First, I would like to mark the first pipe with number 1 and the second pipe with number 2 to make it easy for my calculations. Now, from here, Q1, which is given, equals to 2.5 Q2. And A1 equals 1/2 A2. So I can use these informations to find V1 divided by V2. Now, we know Q1 equals 2.5 Q2, and we know Q1 is A1 times V1. Q2 is A2 times V2. But from the question, A1 is 0.5 A2. So from here, A2 with A2 cancel out, and we can divide it. So here we can say 0.5 V1 equals 2.5 V2. So divided by V2, you can find V1 divided by V2, which is 2.5 divided by 0.5. Therefore, V1 divided by V2, which is 5. Or V1 equals 5 times V2. Thank you so much, and see you in the next part.